Greetings, aspiring scientists. Welcome to my video today on the physical properties of covalent compounds, substances. I know my hair is getting too long. I'll probably cut it this week, so the next video you see, I'll have shorter hair. But for today, it's going to get in my eyes a little bit. Anyway, let's go to my slides. So we are now in 2.2.9. And I didn't really know what to label this, so I'm going to call it the physical properties of covalent substances. Because we're going to include molecules and networks, but we're going to stick to covalently bonded things and try to explain their physical properties. In my previous videos, we have talked a lot about intermolecular forces, London, dipole-dipole, hydrogen bonding, those kind of things. But now we're going to talk about how those properties physically manifest in our world. So let's start with some data. This table has various things, some formulas and structural formulas, molecular mass, dipole moment in units of dBAs, boiling point in Celsius, and then a little subchart that has intermolecular forces, whether it has London, dipole-dipole, or hydrogen bonding. And you could be asked to explain this on like a paper 2 or paper 1B kind of exam, or in quite a lot of textbook homework questions. So let's try to explain this. So I think the point of this table is that all of these compounds that are given here, propane, methoxymethane, ethanal, ethanol, methanoic acid, have very similar molecular mass. It's around 45, between 44 and 46. So they all have London dispersion forces, yes, and all the London dispersion forces should be very similar strength because it just depends on molecular weight and number of electrons, which are very similar in all of these molecules. So we have that, but what we need to explain is these boiling points. They go from minus 42 to minus 24 to 20 to 78 to 100. Some really big jumps there. Okay, so let's go one by one. So between propane, C3H8, and methoxymethane, C2H6O, that has two CH3 groups linked through an oxygen, boiling point goes up by 20 degrees. It's still below zero, but it's much higher than propane. So how do we explain this? We can look at the intermolecular forces and the molecular dipole moment. So the dipole moment of methoxymethane is much, much higher than propane. Propane is almost undetectable, 0.084. But 1.30 for methoxymethane is much more polar. That means it has a permanent dipole. That means it has dipole-dipole intermolecular forces on top of London. That bumps its boiling point up by around 20 points, 20 degrees. Okay, we can explain that. Next, ethanal and methoxymethane. What's the difference here, really? So they have similar molecular mass, similar London forces. They both have dipole-dipole forces. They both don't have hydrogen bonding. But just look at the strength of the dipole again. So 2.69, very strong dipole, very polar molecule, versus 1.3 for methoxymethane. So as you increase the polarity and the concentration of electron density in ethanal, it's going to be able to provide stronger forces, stronger attractive forces with other ethanal molecules around it. That bumps its boiling point up by 45 degrees-ish, up to 20.2, above zero. Okay, we can explain that as well. Let's compare then ethanol with ethanal, C2H4O versus C2H6O. And you can see the structures there. So ethanol had a C double bond O. I think that's also why it has a stronger dipole than methoxymethane, because that has only carbon-oxygen single bonds. But carbon-oxygen double bond means that oxygen has sort of twice as much power to take two pairs of electrons from that carbon and create a region of negative density. Okay, but going back to ethanol versus ethanol, now the boiling point of ethanol is actually a lot higher than ethanal. Even though it has a lower dipole moment. How is that possible? So we've lost the carbon-oxygen double bond. The oxygen isn't pulling quite as much electron density to itself in ethanol, so it has less of a dipole moment, 1.69, and yet its boiling point is much higher. It comes again from the intermolecular forces. Now there is an OH bond in ethanol that can do hydrogen bonding, which I've written on the right. Hydrogen bonding, yes, for ethanol. So hydrogen bonding is very powerful. It'll cause molecules to be very attracted to each other in ethanol, stabilize themselves with hydrogen bonds, pseudo-covalent bonds. They're very strong. So that bumps its boiling point up. We can explain that. Now the last one here might be the most interesting. How are we going to compare methanoic acid with ethanol? They have similar molecular weight, similar dipole. They have all the molecular forces, London, dipole, and hydrogen bonding, and yet methanoic acid's boiling point is still like 22 degrees above ethanol. We have to be able to explain that. And how can we? We've used up all the intermolecular forces and the size and the dipole. But how does hydrogen bonding scale? The only way that it can scale really is the number of positions where it can occur. So if we draw methanoic acid, I want yellow. So methanoic acid looking something like this. A carbon-hydrogen bond, a carbon-oxygen double bond, carbon-oxygen single bond, and oxygen-hydrogen single bond. Now this can hydrogen bond with another methanoic acid, but I'm going to draw it in such a way that we can actually get two hydrogen bonds. Now there's a lone pair. Let me draw all the lone pairs on these. Might help us out. So we're going to have the hydrogen bond here between a lone pair and a positively polarized hydrogen. And that's going to leave us with another hydrogen here. Sorry, I want to make that one an OH. Let me just erase this. OH. Lone pairs here. A hydrogen here. So we can actually have another hydrogen bond here. Okay, so let's just look at the structure for a second. This is kind of forming like a giant ring structure, right? And it's kind of an octagon, I believe. 1, 2, 3, 4, 5, 6, 7, 8. It's an 8-sided ring structure. Which is fairly stable. You know, there's such a thing as cyclooctane, which is just 8 carbons in a ring, fairly stable. But you might ask, why cannot ethanol do this? Let me just write this a bit more clearly. So an 8-sided ring is fairly stable, but if you were to try to do this with ethanol, you could imagine a structure where it happens, but you have to ask, is it going to happen like that? Based off stability and bond angles and things. So we could have this bond with the oxygen of another ethanol. It has an OH group. We could try to make a double hydrogen bond. But what kind of shape is this? It's just a little square, right? Now you might have heard of something called cyclobutane. There actually does exist a carbon compound, cyclobutane, that is just a square with almost 90-degree angles between it and a couple hydrogens on each of these carbons. Now, this has been made, it exists. It's actually not an entirely uncommon structure in a lot of organic molecules, but it is way, way, way less stable than something like a 5-membered ring, or a 6-membered ring, or a 7-membered ring, or an 8-membered ring. And because these carbons want to be 109 degrees, they're actually trying to be tetrahedral geometry, right? But when you force them into a square like this, you're trying to cram them into the square at 90-degree angles. So that's not what they want to be naturally. It's not the most stable angle. Therefore, this structure is not very stable. So 4-sided rings are much less stable. And so this type of hydrogen bonding, double hydrogen bonding in ethanol, doesn't happen as easily as in something like methanoic acid. And I think I researched recently that methanoic acid and ethanoic acid, things with these similar COOH structures, often group up with a partner like this and form dimers, they're called, to exist stably just in the liquid phase or in solution or whatever. So I think this is the best explanation for why methanoic acid has a higher boiling point. It has multiple positions available for simultaneous hydrogen bonding, which form a stable ring structure. Okay, hopefully you got that. I like this table. There's a lot of good information here and comparisons. So let's move on to some other things. The idea of volatility. You guys might have heard this before. If you know chemistry, you know what it means. But in casual everyday language, it kind of means something unstable, right? Like he's got a volatile personality or something. It means unpredictable, unstable, prone to explode, maybe. So in chemistry, though, volatility is the ease with which molecules can enter the gas phase. So we're talking about covalent molecules. Although I think you could sometimes talk about like metals or other compounds being volatile as well, just talking about how easily they enter the gas phase. So covalent networks are crystallized solids with very high melting and boiling points, and basically melting and boiling would destroy the lattice, the crystal of the network. And so when you melt or boil it, you destroy the network, and that means you can look at how much energy it takes to destroy the network, and that's going to be basically related to its boiling and melting point. So covalent molecules, however, have an extremely wide range of boiling points depending on their size and their polarity, as you would expect. Those with hydrogen bonding can have high boiling points, higher than you would expect, and those with many electrons, or just large size, many electrons and high molecular weight, and also long stackable shapes, flat shapes, can have high boiling points and melting points. So anything that has high boiling and melting points has low volatility. They're sort of inversely related. Something with high volatility has low melting and boiling points, low intermolecular forces. What else? Conductivity. We've talked about this a little bit with ionic compounds. So it's the ease with which an electric current, moving charged particles, can flow through. So covalent networks and molecules generally do not conduct electricity, especially compared to other types of bonding that we've seen, or we will see. Electrical conduction or heat conduction generally requires the movement of particles or charged particles, but these molecules are not charged. Covalent molecules don't have a full charge, usually. And their electrons are definitely not free to move through space. They're locked in the molecules and bonds. Some exceptions to this are ions, such as sulfate. You might remember some polyatomic ions I asked you to memorize, I think. So things like SO4 2-, or nitrate NO3-, or phosphate PO4 3-, or ammonium. You can have positive ones as well, NH4+. These are technically covalently bonded compounds, polyatomic ions, but since they're charged, when they move, they will provide electric current and conduct pretty well. Also, networks like graphite, these have delocalized electrons. Every carbon has a double bond, and so there's a highway where those double bonded electrons can travel anywhere on the surfaces. They conduct well. But those are exceptions. Solubility. I talked about this in my video about solutions and concentration. So solubility is how easily something dissolves in a solvent, in a sort of matrix around it. So solubility comes from the concept of like dissolves like. You should definitely remember this, and you'll hear people say this all the time, like dissolves like. That means things with similar intermolecular forces and similar physical properties mix well and dissolve. One can dissolve the other well, we can say. And when it comes to polarity and intermolecular forces, this is what we say, like dissolves like. A molecule is likely to dissolve in a solvent if the forces between the solute and the solvent are stronger than those between the solute molecules themselves. This is hugely important. Okay? So everything comes down to intermolecular forces. If you're ever asked on a test or you're writing a paper or something, you need to explain solubility. It comes down to, do they have similar intermolecular forces, and could the solvents provided intermolecular forces perhaps be an even better fit for the solute molecules? So we can have ideas like polar dissolves polar. So a polar HCl can dissolve well in H2O, which is also very polar. And nonpolar dissolves nonpolar. For example, I2, diatomic nonpolar gas, or solid, sorry. But it is a molecule. It can dissolve in C6H14, which is hexane, a nonpolar, just straight carbon chain of 6 carbons in a row with hydrogens bonded at every available position. But things like I2 will not dissolve well in H2O. Things like HCl will not dissolve well in hexane, C6H14. Their intermolecular forces do not match. And generally, the best way to think about it, I think, is that the stronger molecular forces, like hydrogen bonding and dipole-dipole, sort of dictate what happens, right? So it's not that C6H14 would try to dissolve HCl and can't. It's that HCl is very polar, and it's just very attracted to itself. It's already stable and fine, and so it has no need to interact with something like C6H14. Similarly, if you think about trying to dissolve I2 in H2O, I2 is nonpolar, H2O is very polar and has a lot of hydrogen bonding. Remember, it can have 4 per molecule. So that's what you have to overcome. You need to separate water molecules from themselves before they can surround something else, right? And they're not going to do that. They're going to be already stable and happy hydrogen bonding with themselves. All right, miscibility. This is very related to solubility. Miscibility is related to solubility, but it's more often used to describe mixing liquids. So you guys might know when you try to mix some liquids together, like, I don't know, oil and vinegar, they do not mix very well. They might look like they mix for a few minutes, but then if you leave it, they separate again. Those would be considered not miscible, or immiscible is the word, IMMISCIBILITY. So a pair of miscible liquids can perfectly mix and form a homogeneous solution quickly. That means there's not going to be any pockets or bubbles or dense regions of one liquid versus the other. That's a homogeneous solution. And again, liquids with similar intermolecular forces will be miscible. Examples are water and ethanol. They can hydrogen bond with each other and mix perfectly fine. Hexane and octane, they're just a bunch of London forces trying to mix together there, so they will mix well. They don't have dipole-dipole or hydrogen bonding or anything. Now, molecules with significantly different intermolecular force types will have limited solubility and are considered immiscible, basically if they form layers and they don't form homogeneous solutions. So that word immiscible means not miscible, not able to mix and form a homogeneous solution. So these are the rules you can generally follow, although there will be some exceptions. Like sometimes people ask me, what is milk? And I don't really know how to explain what milk is. I think some YouTubers have some good videos about it, like maybe Nile Red or some other ones I'm thinking of. I can't remember the name, but milk is, I think, what's called colloidal suspension. So there's very small particles of sort of bubbles or pockets where there's London forces happening, and outside of that, dipole-dipole forces happening and hydrogen bonding happening. There's sort of all the forces going on, but they are sometimes enclosed in little bubbles or packs inside the liquid itself. So that's a very complicated situation we don't really talk about in IB, but I want you to know that there are exceptions to some of these as well. Covalent molecules, miscibility. So I do want to go a little bit more into this, and specifically, like when I was talking about milk, I was talking about some regions having mainly London forces and dipole-dipole and hydrogen bonding, maybe inside a pocket, and then outside a pocket is a different force going on. So what's happening there is that we have molecules with different regions that can be labeled hydrophilic. Philic means likes, so likes water. Hydrophilic or hydrophobic means afraid of. You guys maybe know the word phobia, means fear of something. So hydrophobic ones will be the nonpolar sections of a molecule. These tend to avoid things like water, and so they can group up with other nonpolar regions of other molecules and form little pockets. So this is what's going on with soap molecules. You guys might wonder how soap can mix with water and oil and dirt and basically anything you'd want to wash away. It works because it has these regions, hydrophilic head and hydrophobic tail. So when you pour water on yourself, on your skin to wash it, the hydrophobic oil and dirt, usually that's on your hands or whatever on your skin, the hydrophobic regions of the soap will grab onto that and immediately attach and form some London force interactions. But the outside of that, the polar region, has no interest or has no attraction to the hydrophobic dirt and grime on your skin. So it ends up on the outside. But the outside is where water is. You're rinsing it and washing it with water, right? So that water that's moving by will be attracted to the head. It pulls then that little bubble or package or compartment off, and that compartment has a hydrophilic outside interacting with water and a hydrophobic inside interacting with oil and dirt, and it washes away. So structures which do not mix with water are called hydrophobic, and those which do are called hydrophilic. Soaps and detergents are interesting compounds which contain structures of both types on the same molecule, so therefore they can mix with both, and in fact allow several portions of hydrophobic things to dissolve in water. We can actually get nearly homogeneous solutions where there's an even distribution of these little packages of hydrophobic grease and grime. They're so small though you can't see them obviously. They're just surrounded by water on the molecular scale. So here's some examples of soaps. We might have something with like a C double bond O group that's missing a hydrogen, so is negatively charged, and it will come as a salt bonded with sodium. So it's actually an ionic compound. Cation and anion here, even though the anion is absolutely huge with a hydrophobic tail that can help it remain, liquid or solid. But when we mix this with water, the very charged negative hydrophilic end there on the right is attracted to water. The hydrophobic end is attracted to oils and dirts and grimes and things. You could also have a sodium sulfonate soap with kind of a sulfate group attached. Also very polar, hydrophilic. We could have a cation detergent. This one has a positively charged head. It has almost a tri or quatra methyl ammonium group there. And then a hydrophobic tail, very similar to the others before it. But I think some people might even be sensitive to these highly ionic charged soaps. So if you want a slightly less harsh one, you might go with a non-ionic detergent. Ethylene glycol group as the hydrophilic head, and then slightly shorter non-polar hydrocarbon hydrophilic tail. But they all work the same. Hydrophobic tail is attracted to dirt and grime. Hydrophilic head mixes well with water. What else could we consider? Okay, next we could also talk about drugs, both pharmaceutical and recreational. Let's consider something like morphine. This is a chemical compound that acts on the nervous system, in the brain especially, and it has a structure here. This structure is active. This structure fits perfectly into some receptor regions in your neurons and cells. And I think it either blocks or activates something to do with pain, right? Morphine is a painkiller. It's a strong analgesic, I think it's called. And it has a lot of negative side effects like addiction and, interrupting your gastrointestinal tract and making you, very non-hyperactive or I guess lazy. I've never actually tried it, of course, but these are things I've read about. It has the main effect of killing pain, but several negative side effects, and it has the potential for abuse and addiction. Now you can look at other structures here. You might have heard of codeine and heroin as other drugs, which basically they contain the morphine structure. But there's some slight differences. Codeine has an extra CH3 group attached to the top where it used to be an OH group. Otherwise, it's the same. And heroin has, instead of an OH group, has an OCOCH3 group where the carbon in the middle is double bonded to an oxygen. So that one there is called an actual ester group. So what's going on here? Opioid drugs, these are called. These are strong but addictive painkiller drugs. They must be soluble in water because your body is mostly water. So if we want them to be absorbed and go anywhere and do anything, drugs mainly have to be soluble in water because blood is mostly water. But they also need to be able to cross the hydrophobic membrane of the brain to produce their main effect. So there exists this thing in the body called the blood-brain barrier, where there's a hydrophobic, London forest-based sort of hydrocarbon tail chain wall that blocks a lot of polar section containing molecules from passing through. Okay, so if you want anything to actually reach the brain, it needs to be able to pass that barrier somehow. And one of the ways to do that is to make the molecules slightly less polar, less likely to hydrogen bond. So morphine is the absolute worst at crossing this barrier. It has these two OH groups. It's going to be doing a lot of hydrogen bonding, at least doubly hydrogen bonding with water molecules that it's dissolved in the blood. And those water molecules tugging at it with strong attractive forces will not allow it to pass through the blood-brain barrier very well, even though it has nonpolar regions that it can form some intermolecular forces, London forces, attractions with the blood-brain barrier. The OH groups bonded with water in the blood pull it away from that. It can't actually get to the brain very well. What about codeine, though? This has removed a location for hydrogen bonding and replaced it with a CH3 group. CH3 group is much less polar. You still have some strong dipoles on this as well, but this can pass through the blood-brain barrier better than morphine. Problem is, codeine has no effect. It doesn't fit in the receptor. So I think it needs to be broken down back into morphine. That CH3 group at the top needs to be replaced with a hydrogen. But that's something that the body does fairly often, swapping these things that are attached to oxygen. So just getting it through the barrier to the brain is the main issue, and then the brain will break it down into an OH bond, and then it will fit in the receptor and have the pain-killing effect. Okay. Now, if we look at heroin, 2 OH groups are now replaced with C double bond O and CH3 groups. A much larger, much less polar and less hydrogen bonding group. And heroin is the absolute best of these 3 anyway. There's probably even better ones that have been designed. I don't even know, like fentanyl or the newer ones. Can probably pass through the blood-brain barrier even better. But this, now that it doesn't have areas for hydrogen bonding, isn't attracted to the solvent, the blood, as much. It'll pass through the blood-brain barrier, go to the brain, and it does need to be cut up as well. So these groups have to be chopped off and replaced with hydrogen to make morphine again. Then morphine fits in the receptor, and we get a very large, high-efficacy molecule painkiller, but also more potential for addiction and potential side effects. So I think that's why heroin is not really used as a pharmaceutical. It's only used as a recreational drug these days, because it's more dangerous but more euphoric, produces a better good feeling faster. Okay, so summary. Covalent molecules, they are usually volatile, only held together with intermolecular forces. Compare that with networks. Networks are non-volatile, they're solid crystals. Everything is covalently bonded in large structures. Conductivity. Covalent molecules are poor electrical conductors due to the absence of freely moving charged particles except for ions. Covalent networks are usually poor electrical conductors except for graphite-based networks with delocalized electrons. Solubility of covalent molecules really depends on the polarity of groups within the structure and the potential for hydrogen bonding. So polar and charged areas will be able to be surrounded by water and dissolve well. Non-polar regions will not. But you can have molecules that have groups of both types that can mix both with oily things and watery things. Covalent networks are generally insoluble, not soluble in water due to strong covalent crystal structure and minimal intermolecular forces with water. Water can basically only interact at the surface of covalent networks, and if they have no attraction for water, or water is not able to break the strong covalent bonds, there's not going to be any dissolution, no dissolving. And finally, physical strength. Covalent molecules usually have weak physical strength properties, weak crystals, but covalent networks have high physical strength, very high, due to solid phase covalent bonding in expansive interconnected crystal structures. Every atom forms multiple covalent bonds in multiple directions around it. All right, very good to memorize or get a good understanding of this slide. Practice then, what do we have? So first, describe the relationship between volatility and boiling point. As I mentioned before, they're inversely related. Something that has a high boiling point has low volatility. Its molecules do not enter the gas phase very easily. Something with high volatility has a low boiling point. Its molecules easily and frequently enter the gas phase. Second, explain why CH3CH2OH is miscible with water. So this is ethanol. Ethanol, if you look at it, you could say almost has a hydrophilic region and a hydrophobic region. It has an OH group capable of hydrogen bonding with a very polarized carbon-oxygen and oxygen-hydrogen bond region. But it also has a little hydrophobic London force-based nonpolar chain CH2CH3 there. So it actually is able to mix both with water and quite a lot of nonpolar solvents or molecules as well. Third, identify which two of the following substances are readily soluble in water. CH3COH, CH3CH2 6 times, and then CH3 on the end. CH3CH2 6 times, CH2OH, and CH3COCH3. Okay, we might want to draw the structures for these, but we only have two choices for what's going to be readily soluble in water. So our first one here, I'm just going to draw skeletal structures. This is ethanoic acid, COOH structure. B, we've basically just got a long carbon chain. 1, 2, 3, 4, 5, 6, 7, 8 carbons in a row. C, we've got that, but on the end, an OH group. 1, 2, 3, 4, 5, 6, 7, 8 OH. And then D is going to be some carbon change with an oxygen. So CH3 O CH3. Just like that. Okay. So you can probably identify that B is not going to be readily soluble in water. It is completely nonpolar London force based in its intermolecular forces. Water is going to keep hydrogen bonding with itself rather than mix with this at all. So we can eliminate that. The next choice is not so easy though. I think we can definitely say that A will be readily soluble in water. It has two locations for hydrogen bonding. It's very polar. It doesn't have a long nonpolar chain or region. So this should be very soluble. So what about C versus D? C has a location for hydrogen bonding, but it also has 1, 2, 3, 4, 5, 6, 7, 8 carbons in a hydrophobic tail. So you kind of have to ask the question, how long can that tail become until the London forces become more significant than the hydrogen bonding? And I think if you think about it, based on things you've heard or worked with or experienced, methanol definitely mixes with water. Ethanol definitely mixes with water in our alcoholic drinks. Propanol mixes with water in things like disinfectants. Butanol, you probably haven't worked with as much, but I think it still mixes with water. But as you get up to pentanol, hexanol, heptanol, octanol, there's going to be a point somewhere in there where suddenly the nonpolar regions and the London interactions become much more significant than that small area where a hydrogen bond is available. And those nonpolar hydrophobic tails will prefer to stick together with themselves rather than allow any water to enter that liquid phase layer. So I'm going to say I don't think this readily mixes with water. It's too long of a hydrophobic chain. All right, and then D, CH3COCH3. This is a polar molecule with some carbons that provide nonpolar regions, but very similar to something like ethanol from number 2. This should also be miscible with water due to its ability to offer a hydrogen bonding acceptance through a lone pair on this oxygen and have short or not very significant London force hydrophobic regions. So this should be soluble in water. All right. So I think that's all I have for today. Hopefully you learned something and you'll be able to explain why things mix or dissolve or interact with each other based on their intermolecular forces. So I think next time we'll talk a little bit about chromatography, which is how to separate and identify covalent compounds based on some of the physical properties we've talked about in today's lesson. If I don't see you again before January 1st, then Happy New Year, have a good 2026, and I'll see you next time. Bye-bye.